Hello everyone. In this video, you will learn how to determine the maximum moment in the beams, part 6, with different loading scheme, including the following key points that we are going to cover in this video on how to determine the support reactions, drawing the shear force and bending moment diagram, and we will also cover to how to explain the simplified approach to find the maximum moment using the shear diagram and the method subsections. So let's dive into our problem. Determine the maximum moment of a beam carrying a uniform load and a concentrated load assumed in the figure below. So we have here, as you can see in this figure, we have a load diagram, 5.5 span of the beam, and 1.5 cantilever end, and it's loaded of 60 kilonewton per meter uniform load, a concentrated load of 45 kilonewtons, and we have also 15 kilonewtons per meter applied at the cantilever end, and a concentrated of 4 kilonewton load at the free end. So let's get started with our solution. First of all, before we can start to draw the shear diagram, we need to find first the reaction at the support. So we can choose any arbitrary location at point A or B. So let's say at summation moment at A, positive clockwise is equal to 0. So we have 60 kilonewtons per meter times 3.5 square over 2, which is the uniform load here, times 45 kilonewtons times 1.5, that is positive, which is clockwise with respect to point A, minus RB, that is the reaction at point B, times 5.5, the moment arm, plus 15 times 1.5, that is the uniform load at the cantilever end, times 6.25, which is the lever arm from point A to the center of uniform load, 15 kilonewtons per meter, somewhere here, plus the 4 kilonewton times 7 meters, that is the moment arm from point A to E, which is 7 meters, and that is equal to 0. So to calculate the RB, that is equal to 109.75 kilonewton. Now, to determine the reaction at point A, if we sum up forces positive upward, which is equal to 0, we have 109.75 kilonewton plus RA, positive upward, minus 60 times 3.5, that is due to the uniform load downward, and negative 45 kilonewtons downward, and 15 kilonewtons meter times 1.5, which is downward, and a 4 kilonewton concentrated load at the free end equal to 0. So to calculate a reaction at point A, that is equal to 171.75 kilonewton. So now we are done with the reactions at point A and B. We can now start to draw the shear and shear diagram. So at point A, that is equal to the reaction at A, that is the shear at this point. So between A and C, we have a uniform load of 60 kilonewton, which is zero slope. So we have linear here in the shear diagram, which is first degree from point A to C. So at point C, that is equal to 171.75 minus the area between A and C, which is uniform load, 60 kilonewtons per meter. So the shear at point C, that is 171.75 minus 60 times 1.5 meters is equal to 81.75 kilonewtons. So that is the one here. That is the shear just to the left of point C. Now at point C, we have a concentrated load of 45, which is downward. So it will drop down from 81.75 to 36.75. So this is the shear just to the right at point C. Now, the shear at point D, that is equal to 36.75, not this one, this is 36.75, minus the load between C and D. So the only load that we have between this point C and D is only 60 kilonewtons per meter, which is 2 meters length, and that is equal to 83 by negative 83.25. So we have here the calculation, 36.75 minus 60 times 2, that is 2 times 2, equal to negative 83.25 kilonewton. So again, this is the uniform load, zero shear. So we have first degree in the shear diagram that is linear at this point. So from point B is equal to the shear at point D, but between D and B, there is no load. So zero load, that is in the shear is constant. So meaning if you cut any section between D and B, the shear is constant. That is zero slope between D and B. So now, to calculate the shear at B, that is equal to negative 83.25 plus the reaction at point B, which is 109.75, and that is equal to 26.5. That is positive. So according to this calculation, we have here negative 83.25 plus 109.75 kilonewton, and that is equal to 26.5 kilonewton. So that is the shear just to the right of point B, which is also equal to the shear at the cantilever end. So to calculate the shear at point E, that is equal to 26.5 minus the load between B and E, which is equal to 26.5 minus 15 times 1.5 due to the uniform load minus 4. So it's equal to 0. So if it happens that they are not equal to 0, then you just check the preceding calculation, if just in case there is some inconsistency here. So now we are done with the shear diagram. We can now proceed to draw the moment diagram. So to draw the moment diagram, the maximum moment can be determined by calculating the area under the shear diagram, starting from the point 0 shear. So at point A, moment is equal to 0. Whether it is spin or roller, there is no moment at point A. Now at point C, that is equal to the area under the shear diagram. So in the shear diagram, we have a trapezoidal area, and that is equal to 0.5 times the length, which is 1.5 meters, times the average of 171.75 and 81.75. So that is the area of the trapezoidal, which is equal to 190.1 kilonewton meters. So that is, we have here 190.1. Now to determine the maximum moment at this point, we need to determine this distance. So I have calculated that distance by ratio and proportion. we have this x 2 meters. This one is extracted from this portion here. So this is how we come up this 0.61 by ratio and proportion. So I don't need to elaborate too much on this one because it's very self-explanatory, and it is just a straightforward calculation. So we have x is equal to 0.61 meters. So the maximum moment is just equal to 190.1 times the area of this small triangle here. So the area is 1/2 bh, that's equal to 190.1.5 times 0.61 times the height 36.75. The height of this small triangle is 36.75. So the maximum moment is equal to 201.3. This is the moment at this at zero shear. So if you can see here in our shear diagram, this is linear first degree. So our moment diagram is second degree from this point to that point. That is parabolic. So the shear is positive. The slope in the moment diagram is also positive, and it is incrementally reducing until it reaches to the zero shear, which is the slope is zero. And this point is what we call a contraflexure, the transition between the positive slope and the negative slope. Now, to calculate the moment at D, we will calculate this point by point in order to plot the moment diagram. So to determine the moment at point D, in the same manner, just equal to 201.3, and again, plus the area between this point to that point. What is that area? This is triangle. So that area is equal to 201.3 minus, because that is negative shear, times 0.5 times 1.39, that's the length from here to there, 1.39, times 83.25, which is this one. That is equal to 143.4. So that is the moment at point D. Now to calculate the moment at point B, and that is equal to 143.4 times the area between D and B. So 143 minus the area between D and B, 83.25 times 2, 83.25 times 2, that is the 2 meters length, and that is equal to negative 23. And this value, negative 23, should be equal also if we take a sum up moment at the face of the cantilever beam. If it so happens they are not equal, then you will need to check the calculation. Maybe there is some error or something or mistake. So the difference, this moment at point B is equal to minus 23 plus the area under the shear diagram, which is equal to 0. So if you can notice, notice here at cantilever end we have negative 22.9, and we have here 23. Actually, this is 23.1. So the small discrepancy is that's fine, because that is due to the rounding up of numbers. And the other way of determining the maximum moment, guys, is what we call section method. So the important thing here, this is the alternative ways to determine the maximum moment. If we extract the beam, if we cut the section here where we have the shear is 0, and that is always the location of our maximum moment. So if we extract the moment, the beam, if from point A to 2.11 meters, that is from here to there where the shear is 0, we have this one. We have the shear and we have the moment. So to take the moment, by summing up moment at this location, that is positive clockwise, so maximum moment is equal to 171.75, which is this one here, the reaction of A, times 2.11 minus 60 times 2.11 squared over 2. That is due to the uniform load. Minus 45 kilonewton times 0.61, that is counterclockwise. That's why this 2 here is negative. So the maximum moment is equal to 201.3, that is kilonewton meter. So the same result that you will get here in from the area under the shear diagram. So you have two options. Which one is more comfortable for you to calculate the maximum moment? But if you are just after to determine the maximum moment, once you determine the location of zero shear, then you can sum up directly the section method, and you don't need to draw the rest of the shear diagram and the moment diagram to save your time. So finally, guys, the final result of our maximum moment, we have a positive moment and negative moment, which is 201.3 and negative 23, and negative moment there, and the governing is the positive moment. So if there's if just in case there's a lot of zero shear here along the beam, so by own engineering judgment, which one gives maximum moment, maybe you can by visual inspection, the heavier load, that is gives you an idea that the location of maximum moment. So that's all guys for this video. Thank you very much for watching, and if you find this video helpful, please don't forget to like or subscribe so that you will be updated for the next upload. Thank you very much. See you next time. Bye bye and God bless.